Real numbers. Properties of positive integers. The fundamental theorem of arithmetic. Revisiting irrational number and rational numbers and its expansion. The fundamental theorem of arithmetic. Every composite number can be expressed or factorized as a product of primes, and this factorization is unique, apart from the order in which the prime factors occur. For instance, 2 is equal to 2, 4 is equal to 2 into 2, 253 is equal to 11 plus 23, and so on. The prime factorization of a natural number is unique, except for the order of its factors, that is, 2 into 3 into 5 into 7 as the same as 3 into 5 into 7 into 2. In general, given a composite number x, we factorize it as x is equal to p1, p2, and so on pn, where p1, p2, and so on pn are primes and written as in ascending order. If we combine the same primes, we will get powers of primes. For example, the prime factorization of 32760 is 2 into 2 into 2 into 3 into 3 into 5 into 7 into 13. We can write this factorization as 2 cube into 3 square into 5 into 7 into 13. Consider the number 4n, where n is a natural number. Check whether there is any value of n for which 4n ends with the digit 0. Solution. If the number 4n for any n were to end with the digit 0, then it would be divisible by 5. That is, the prime factorization of 4n would contain the prime 5. This is not possible because 4n is equal to 2 into bracket 2n. So, the only prime in the factorization of 4n is 2. Therefore, the uniqueness of the fundamental theorem of arithmetic guarantees that there are no other primes in the factorization of 4n. So there is no natural numbers n for which 4n ends with the digit 0. Find the LCM and HCF of 6 and 20 by the prime factorization method. We have 6 is equal to 2 raised upon 1 into 3 raised upon 1, and 20 is equal to 2 into 2 into 5, that is 2 square into 5 raised to 1. You can find HCF of 6 and 20 is equal to 2 and LCM of 6 and 20 is equal to 2 into 2 into 3 into 5 is equal to 60 as done in your earlier classes. Note that HCF of 6 and 20 is equal to 2 raised to power 1. Product of the smallest power of each common prime factor in the numbers. LCM of 6 and 20 is equal to 2 square into 3 into 5. Product of the greatest power of each prime factor involved in the numbers. Find the HCF of 96 and 404 by the prime factorization method. Hence, find their LCM. Solution. The prime factorization of 96 and 404 gives 96 is equal to 2 raised to 5 into 3. 404 is equal to 2 square into 101. Therefore, the HCF of these two integers is 2 square is equal to 4. LCM 96 and 404 is equal to 96 into 404 upon HCF 96 and 404 is equal to 96 into 404 upon 4 is equal to 9696. Revisiting irrational numbers. A number S is called irrational if it cannot be written in the form P upon Q, where P and Q are integers and Q is not equal to 0. Let P be a prime number. Prove if P divides A square, then divides A where A is a positive integer. Proof. Let the prime factorization of A be as follows. A is equal to P1 into P2 into Pn, where P1, P2 and Pn are primes, not necessarily distinct. Therefore, A square is equal to into bracket P1 into P2 into Pn into bracket P1 into P2 into Pn is equal to P1 square into P2 square into Pn square. Now, we are given that P divides A square. Therefore, from the fundamental theorem of arithmetic, it follows that P is one of the prime factors of A square. However, using the uniqueness part of the fundamental theorem of arithmetic, we realize that the only prime factors of A square are P1, P2 up to Pn and so on. As Pn square is equal to Pn into Pn, so P is one of P1, P2 up to Pn. Now, since A is equal to P1 into P2 into and so on into Pn and P is one of P1, P2 and so on Pn, P divides A. Theorem: square root 2 is irrational. Proof: let us assume to the contrary that square root 2 is rational. So, we can find integers r and s is not equal to 0 such that square root 2 is equal to r upon s. Suppose r and s have a common factor other than 1, say b. Therefore, assume we get square root 2 as square root 2 is equal to a upon b, where a and b are co-prime. So, b square root 2 is equal to a. Squaring on both sides and rearranging, we get 2b square is equal to a square. Therefore, 2 divides a square. Now, by theorem, 2 divides a 2. So, we can write a is equal to 2c for some integers c. Substituting for a, we get 2b square is equal to 4c square. That is, b square is equal to 2c square. This means that 2 divide b square and so 2 divides b too. Therefore, a and b have at least 2 as a common factor. But this contradicts the fact that a and b have no common factors other than 1. This contradiction has arisen because of our incorrect assumption that 2 is rational. So we conclude that 2 is irrational. Show that 5 minus square root 3 is irrational. Solution: Let us assume, to the contrary, that 5 minus square root 3 is rational. That is, we can find co-prime A and B where B is not equal to 0 such that 5 minus square root 3 is equal to A upon B. Therefore, 5 minus A upon B is equal to square root 3. Rearranging this equation, we get square root 3 is equal to 5 minus A upon B is equal to 5B minus A upon B. Since A and B are integers, we get 5 minus A upon B is rational, and so square root 3 is rational. But this contradicts the fact that square root 3 is irrational. This contradiction has arisen because of our incorrect assumption that 5 minus square root 3 is rational. So we conclude that 5 minus square root 3 is irrational. Revisiting rational numbers and their decimal expansions. In this section, we are going to consider a rational number, say P upon Q, where Q is not equal to 0, and explore exactly when the decimal expansion of P upon Q is terminating and when it is non-terminating, repeating, or recurring. We do so by considering several examples. Let us consider the following rational number, 0.375. Now, 0.375 is equal to 375 upon 1000 is equal to 375 upon 10 cube. This is expressed as rational number whose denominator is powers of 10. Let us try and cancel the common factors between the numerator and denominator and see what we get. 0.375 is equal to 375 upon 10 cube is equal to 3 into 125 upon 10 cube is equal to 3 into 5 cube upon 2 cube into 5 cube is equal to 3 by 2 cube. 2 and 5 are only two prime factors of 10. Therefore, we can get denominator either 2 is power or 5's power or both. So cancelling out the common factors between the numerator and the denominator, we find that this real number is a rational number of the form PQ, where the prime factorization of Q is of the form 2 raised to power n into 5 raised to power m, and n, m are some non-negative integers. Theorem: let x be a rational number whose decimal expansion terminates. Then x can be expressed in the form P upon Q, where P and Q are co-prime. And the prime factorization of Q is of the form 2 raised to power n into 5 raised to power m, where n, m are non-negative integers. 3 upon 8 is equal to 2 upon 2 cube is equal to 3 into 5 cube upon 2 cube into 5 cube is equal to 375 upon 10 cube, that is 0.375. This example shows us how we can convert a rational number of the form P upon Q, where Q is of the form 2 raised to power n into 5 raised to power m, to an equivalent rational number of the form A upon B, where B is a power of 10. Let x is equal to P upon Q be a rational number, such that the prime factorization of Q is of the form 2 raised to power n into 5 raised to power m, where n, m are non-negative integers. Then x has a decimal expansion which terminates. Let x is equal to p upon q be a rational number, such that the prime factorization of q is not of the form 2 raised to power n into 5 raised to power m, where n, m are non-negative integers. Then x has a decimal expansion which is non-terminating, repeating or recurring. So that is all about this subtopic and lesson.